Chapter number 12 is going to move us into stoichiometry. And stoichiometry, really, it's the math of chemistry. When you think of the word arithmetic, of course, it's kind of an intimidating word, but again, all it really means is math. Stoichiometry, again, you know that again, a certain amount of ingredients are required to make certain foods or certain recipes. How much you can make is dependent on how much of each ingredient you have. Chemical reactions are much the same way. You can only produce as much product as you have of your individual reactants. Stoichiometry, it's the study of quantitative relationships between amounts of reactants used and the products formed by a chemical reaction. One other thing that I can throw in there that isn't in this definition is energy. When we look at exothermic and endothermic energy, again, certain amounts of energy will be produced. Certain amounts of energy will be required in that production of that product. It's really, like I said, the mathematics of chemistry. Stoichiometry, it is based on the law of conservation of mass, which, if you remember, the law of conservation of mass just states that mass cannot be created nor destroyed. Again, last chapter we talked about 4 representative particles. We talked about atoms, we talked about molecules, formula units, and ions. We're only going to look at the first 3. And the reason why we are not going to look at ions is because ions cannot stand by themselves. Ions, it's positive, it's negative, one gaining electrons, one losing electrons. But again, you can never just have something gaining electrons all by itself. Atoms can be by themselves. Molecules can be by themselves. Formula units, they can also be by themselves. But again, ions will not be represented by themselves. Atoms, it's a single particle element. When you look up on the periodic table or any single element up there by itself is going to be classified as an element. Gold, Au, okay, it's an atom. Sodium, it's an atom. Copper is an atom. Sulfur is an atom. Molecules, on the other hand, these are compounds formed from covalent bonds. And remember what we said a covalent bond was. A covalent bond was 2 or more nonmetals. C6H12O6, that's a molecule. H2O is a molecule. NO2 is a molecule. Also, your diatomic elements. Okay, remember the diatomic 7 and how you find them. H2, O2, F2. All of those are also going to be molecules. Formula units, these are the ones formed from ionic bonds. And remember what we said an ionic bond is. An ionic bond was something that was formed between a metal and a nonmetal. Formed from a positive ion and a negative ion. And the other one that I don't have listed up there is, remember what we said about acids. They were H plus donors. Because I say H plus means an ion. And again, if it is an ion, then acids are also going to be formula units. You're going to need to be able to describe a chemical equation on the atomic level, the molar level, and in terms of the law of conservation of mass. Here's an example. It says solid iron reacts with oxygen gas to produce solid iron 3 oxide. Here are the 4 things I need you to do. Describe it in terms of particles. Describe that reaction in terms of moles. Describe that reaction in terms of law of conservation of mass. And then the final step really kind of goes back to that law of conservation of mass, is show that mass is completely conserved. First thing, here's the chemical equation. But remember what I told you. Every single thing from now on when you look at chemical equations has to be balanced. So going through and balancing this, I get 4Fe plus 3O2 goes to Fe2O3. First thing I said to do, describe it in terms of particles. Okay, Fe, completely by itself, that means it is an atom. Okay, oxygen's a nonmetal, and you might say, oh, I see oxygen on the periodic table, but when I look right here, O2, and I told you diatomic molecules, those are going to be molecules. Fe2O3, metal, nonmetal, that's going to be a formula unit. So when I look here, I've got 4 atoms of Fe. Okay, the coefficients are going to tell you how much you have. I have 3 molecules of O2, and then what that forms is 2 formula units of Fe2O3. Now it says describe it in terms of moles. This is the easy one. We don't even have to worry about what they are. Same thing, but instead of using the words atoms, molecules, formula units, we're just going to put in moles. 4 moles of Fe plus 3 moles of O2 goes to 2 moles of Fe2O3. Next thing I said, describe it in terms of the law of conservation of mass. I'm just going to add up what all the mass is. I'm going to take 4 times what iron's mass is. I'm going to take 3 times, okay, O2, okay, 2 oxygens, 1 oxygen 16, so 2 oxygens is going to be 32, 32 times 3, okay, and then Fe2O3, add all of that up. So iron by itself, I'm going to get 223.4. Oxygen, 96. And then on the product side, I'm going to get 319.4. The last step just says basically prove that everything's conserved. So when I take the 223.4 and the 96, add those together, I get 319.4 on the reactant side, and I get 319.4 on the product side. Last thing is going to be mole ratios. Again, this is going to seem tedious for you, but again, it's getting you in that idea when we start to calculate the stoichiometry problems. When we actually go through some calculations to figure out products produced, reactants needed, and stuff like that. It says, what information does a chemical reaction tell you? Well, if you remember, I told you it tells you the elements or compounds that are present, but more importantly, it tells you the ratio to one another. So when I look at 4 Fe plus 3O2 goes to 2 Fe2O3, same equation that we had. And I say, I need you to list for me what the possible mole ratios are going to be. This is a lot like the FOIL method, okay? What I have to do is I have to set everything equal to one another. So what I'm going to do is I'm going to have iron going to oxygen. So I can put up there 4 moles of Fe to every 3 moles of O2. I also got to take Fe and set it to the compound. So 4 moles of Fe to 2 moles of Fe2O3. Okay, so I got that one done. So now let's go to oxygen. So we're going to go oxygen there, oxygen there. So I get 3 moles of O2 to every 4 moles of Fe, and I get 3 moles of O2 to every 2 moles of Fe2O3. And finally, I got to take the Fe2O3, and I have to go there. I have to take the Fe2O3 and go there. So 2 moles of Fe2O3 to every 4 moles of Fe, and finally 2 moles of Fe2O3 to every 3 moles of O2. Now you won't have to do this for every problem once we actually get into the stoichiometry, but what I'm saying is it's going to allow you to figure out what individual ratios are present and how many of them there are. When I look at this problem, I actually count 6 points, 6 individual ratios. The one thing though that I want to stress is even though I have right here a 2 and a 4, never reduce them down. I want you to actually use that whole mole ratio so you're not getting confused on the coefficients. Math will always still work out, okay? But again, use the real mole ratios.